Okay, in this lecture we're going to extend what we've done up to this point, which is primarily focused on 1D problems, to scalar field problems in 2D. So a few examples, at least a couple examples are given here. One is, let's say you have an insulator. So you have a capacitor with a crack in it. Maybe this is air or a vacuum. You have a couple of electrodes. If you put an electric potential across this, the electric field lines will go around the crack. So I'll talk about the PDEs that govern this and how we can solve those PDEs using the finite element method. It turns out the same PDE will solve potential flow over some solid boundary. Now there are certain approximations to the flow. Hence, if you're familiar with potential flow, the fact that it's irrotational means that you've made certain approximations. But in those limits, you can solve this with a simple scalar potential. Another example not shown is membranes. So in certain biological applications, certain things like parachute deployment, membrane mechanics becomes important. So in the small displacement, small rotation approximation, you can solve these problems using the same PDE. And to do that, we start with defining a scalar potential. So this may be an electric potential with units of voltage. It could also be temperature. You can solve Fourier's equation to get these the field lines we shown earlier. They would be heat transfer lines. But specific to electrostatic problems, we have an electric field. This vector is the gradient, the negative gradient of the potential. Alright, so here I'm talking about electric field. It could be flow velocity, it could be a chemical flux, or mu would be your replaced with phi as your chemical potential. So here's the governing equation. We're going to again use U as the potential. So this is scalar potential, just like phi or mu, and we substitute that into this relation. So we have some constant. You take the gradient and you take divergence, and then there may be some source term. So this source could be a number of things. We'll talk about some physical examples in a moment, but it could be internal heat generation, it could be internal charge density, could be some internal flux due to some external effect if it's a chemical flux problem. Alright, and other thing to note is we're just going to define this as a single constant. So that means it's isotropic. So that means if you have flow in any direction, it has the same properties. Now, if you do the more general case, which I'm showing down here, this is given in Reddy's book, where this is a second order tensor. So these, well, it's given right here. So here is your gradient in the x, in the y, again gradient in x and y, where we've taken divergence. So you get a second order PD with a source term. Alright, one important, very important thing. Remember, from 1D problems, we set this up and do an integration by parts, and that gives us the weak form. In 2D it's a little bit more complicated. Yeah, you can't just extend it exactly the same way to do integration by parts. Instead, we do apply what's called divergence theorem, and I'm not going to go through the proof. This is just something you'll have to remember. What I have on this side is a vector f1. I'm multiplying it times some weight function w. here's my unit normal in the x direction. Here is the contour around the area, and over here I'm taking the gradient of this entire thing over the area. So given this identity, a similar identity for the y direction, we can simplify this PDE down to get it into a weak form, just like, or very similar to the 1D problem. And here I've given the definition of the unit normal with the x and y components. So we'll show in a moment how this contour integral leads to the finite element boundary conditions that's given in the weak form. If you look in the book, this is related to equation 8.28. These boundary conditions we'll find look like the following. So this is a flux. So you have your unit normal in the x, you have these gradients of the potential, and then in the y you have these gradients. So imagine if you simplified this down to an isotropic case. This term would be 0. A11 would equal A22, and you would have unit normal x, gradient of u and x, unit normal y, gradient of u and y. So basically what this gives you is heat flux, let's say for a heat transfer problem, heat flux in the x direction, heat flux in the y, if this was temperature. This is just the thermal gradient times the conductivity constant. It gives you heat flow. What I'm showing here is some domain. So say you want to solve internal temperatures. So you build up these elements, you continue building this up through the entire domain, and then on this surface you're going to have some boundary conditions. You may know the flux coming in, or you may know the temperature, and of course you know the unit normal from geometry. Alright, so let's talk about how we approximate this problem. So how do we solve for this scalar potential? So as we did in the 1D case, we're going to approximate it with displacements over an element, and that element will have J1 to N nodes on it. So one example is here, you'd have 1, 2, 3, 4. So say a 4-node quadrilateral element. These are the solutions at those nodes, and here's the interpolation. So now this is a function of x and y. So that interpolation will give you the estimated solution anywhere inside this element given 4 nodal solutions. So our challenge is solving these unknowns on the nodal solution. And what this will end up looking like is an equation of a matrix equation. K, here's your nodal solutions. At every node you may have some internal source terms, like I mentioned, maybe internal heat generation, and you may have heat transfer on the boundary. Okay, so what I'm showing here is how we're going to define the weak form. Alright, so if you want to reference your book, if you start with 821, what Reddy does is defines these two vectors. This is terms inside the PDE, so you got your gradient on U, you've got your material coefficients, and then that weak form simplifies down to this. Okay, so this is the general form of the PDE, where we've taken the PDE, multiplied times a weight function, and now we're going to apply divergence theorem. So our goal is to reduce the derivatives, modify the derivatives on these two terms, and apply derivative over W. So given this identity, a product rule gives you these two equations. So instead we can substitute in these relations, and using divergence theorem we're left with this, right? So notice now we have a set of boundary conditions along the contour. These are called natural boundary conditions, just like before. in the 1D case. So here's Qn. You have F1 and F2 times my unit normals, and again examples is one is heat flux, where these are thermal conductivities.